Hello everyone, welcome to Gudsky Research Foundation's Applied AI and Machine Learning Educational Series. I am Sunanda and today I will be present video 27 of our 6-month free AI&ML educational series. Before we begin, let me briefly tell you about Gudsky Research Foundation. Gudsky is a non-profit research and educational foundation dedicated to providing free high quality AI education for students, freshers and working professionals. Our mission is simple to make AI and machine learning accessible to everyone, regardless of background. Over the next 6 months, we'll take you through everything from basic data understanding to building intelligent systems. It's completely free of cost. In today's session, we are going to explore one of the simplest yet most powerful algorithms in machine learning. So, that is naive Bayes, also known as probability based classifier. By the end of this video, you will understand how naive Bayes works, how to compute probabilities, and why this model continues to be one of the most efficient algorithms used in analytics, spam detection, sentiment analysis, and much more. So, let's dive in. So, why probability in machine learning? Now, before we jump into the naive Bayes model, let's understand why probability is even needed in machine learning. So, okay, in the real world, data is never perfect. It's often uncertain, noisy, or incomplete. Imagine we are trying to predict if an email is spam or not. Sometimes even a human can't 100% sure. So there is always a bit of uncertainty. So that's where probability comes in. It helps us quantify uncertainty. For example, instead of saying this email is spam, we say there is a 90% chance this email is spam. So that's the magic of probabilistic reasoning. It gives us confidence levels instead of just binary answers. This is achieved using something called Bayes' theorem, which allows us to update our belief whenever new data comes in. So, okay, think of it like this: you believe it might rain today. So, that's your prior belief. But as the day progresses, you see dark clouds, that's new evidence. Now, you update your belief: okay, it's more likely to rain. That's exactly how Bayesian reasoning works in AI, learning from new evidence and adjusting predictions accordingly. So, probability helps ML models think logically under uncertainty, and that's the foundation of naive Bayes. So, now we'll move to the next slide. Like, why naive Bayes? So now that we understand the role of probability, let's talk about why naive Bayes is so popular. Naive Bayes is one of the simplest machine learning algorithms, but don't let that simplicity fool you. It's fast, scalable, and surprisingly powerful. So let's break it down. Like fast and scalable, that means it works even when you have thousands of features, like all the words in an email or document. And data efficient, it doesn't need tons of training data to perform well, ideal for text data. That's why it's widely used in spam filters, sentiment analysis, and document classification. For instance, imagine a spam filter that learns probabilities like, so P of free free mod spam, that equals to 0.9, P of free that is not spam, okay, that is 0.1. So if the word free appears in an mail, naive Bayes will lean toward calling it spam, okay, even though it assumes that all words act independently, which is not always true. It still performs amazingly well in real life text data, and that's why it's often used as a benchmark model to compare against more complex algorithms. So, in short, it is simple, interpretable, efficient. That's called naive Bayes. Okay, and this is why naive Bayes is such an important for machine learning. And if we see the next slide, machine learning context. Now let's place naive Bayes in the broader context of machine learning. So naive Bayes belongs to the supervised learning family. So specifically for classification task. That means it learns from label data, examples where we already know the category or class. For example, if you give the model 1000 emails labeled as spam or not spam, it will learn the probability patterns that distinguish one from the other. Once trained, it can predict the class of a new email based on those learned probabilities. So, here is how it works step by step. Okay, it learns the prior probability of each class, like how many emails are spam or not spam, and in, in next step it learns the conditional probabilities. For example, how often the word offer appears in spam emails, and for a new email it calculates the posterior probability, which means which class is more probable given the word in that mail. Okay, and next step it picks the class with the highest posterior, that's called the maximum a posteriori map rule. So it is a map rule. So it's often compared with decision trees, but while trees make rule based decisions, right? So actually decision trees makes the rule based decisions, and so instead of hard yes or no rules like decision trees, neighbors make decisions probabilistically based on the given evidence. Okay, and if we go to the next slide, agenda. So before we go deeper, here's a quick roadmap of what we'll cover in this video. So Bayes theorem basics, the foundation of probabilistic learning and how beliefs are updated with new evidence. And that means, so it is actually previously we discussed about the foundation of probabilistic learning. It works on probabilistic learning and with the evidence. And naive independence assumption means, and why we call it means, how that simplification helps in computation. Okay, and likelihood and posterior computation, like understanding how probabilities are calculated for each class, and the types of naive Bayes models, that is Gaussian, multinomial, Bernoulli, when and how to use each, and strengths, weakness, and real world applications where naive Bayes shines and where it struggles. So this is what the agenda for this today's session. By the end of the video, you will not only understand how naive Bayes works mathematically, but also how to apply it practically, whether it spam filtering, sentiment detection, or even medical diagnosis. So now we'll see the exactly what is Bayes theorem. So alright everyone, now that we have seen why probability matters in machine learning, let's dive into the core mathematical foundation behind naive Bayes theorem. So what exactly is Bayes theorem means? It's a formula that helps us update our beliefs when new evidence appears. So okay, now think this way, before seeing any data you already have some prior belief, like I think it might rain today, but then you see dark clouds, that's new evidence. So you revise your belief, okay, now I am more confident that it will rain. Mathematically, Bayes theorem does exactly that. It connects the what we already know with what we just observed to compute an updated probability. So exact the formula is for the Bayes theorem, P of H of E equal to P of E of H into P of H by P of E. So where P of H mod E is a posterior probability, that means our updated beliefs after seeing the evidence, and P of E mod H is the likelihood, how likely is to see that evidence is the hypothesis were true. P of H is the prior, what we believed before seeing any data. P of E is the evidence probability, a scaling factor that ensures everything adds up to 1. Okay, so in simple words, Bayes' theorem takes your prior belief, multiples it by how likely the evidence is, and gives you an updated, more accurate belief. So, this concept is everywhere from weather forecasting to medical testing and even spam detection. Once you understand this, the whole naive Bayes algorithm becomes much easier. And terms in naive Bayes theorem. Now let's break those terms down again, but in an even simpler real world way. Imagine you are a doctor diagnosing a disease based on a test result. So in prior, like P of H, this is your initial assumption before the test. Maybe you know that 1% of people have the disease. Likelihood, P of E mod H, this is the probability of observing a positive test result. If a person really have the disease, let's say the test is 90% accurate, so P E mod H equal to 0.9 of chance, and evidence P of E, that means this represents the total probability of getting a positive test result, whether the person has the disease or not. And if we see posterior P of H mod E, this is what we actually want, the probability that the person actually has the disease after testing positive. So putting all it together, posterior equal to likelihood into prior by evidence. It's like saying giving the test result, like test result means evidence. How should I update my belief about the disease? So this process of belief revision is the essence of Bayesian learning, and naive Bayes simply automates this with data. Think of it like a GPS recalculating routes. When new traffic information comes in, it keeps updating its belief about the best path. Okay, and if we take a example data set like playing tennis, here, like let's understand Bayes theorem in an intuitive example. 1% of people have a certain disease. The test of it is 0.01, that means 1%. Now let's say there is a medical test that's 90% accurate. If a person has the disease, the test is 90% of the time. So P of positive mod disease equal to 0.9, but sometimes even healthy people get a false positive. That means P of positive mod no disease, that is 0.1 chance. Now the big question is, if a person test positive, what's the actual chance they really have the disease? So using Bayes theorem, like P of disease mod positive equal to, as given in formula, if we calculate like 0.19 into 0.01 plus 0.1 into 0.99, that equal to, we get the answer like 0.009 plus 0.099, that equal to 0.108. So P of disease that actually positive equal to 0.009 by 0.108, that approximately 0.83. Now if we see the example data set, that is medical test scenario, as it is not play tennis. So let's make this even clear with an example. Suppose only 1% of people in a population have a certain disease, like that means P of disease equal to 0.01. Now let's say there is a medical test that's 90% accurate. If a person has the disease, the test is 90% of the time, P of positive mod disease equal to 0.9. But sometimes even healthy people get a false positive. That means P of positive mod no disease, that is 0.1. Now the big question is, if a person tests positive, what's the actual chance they really have the disease? So using Bayes theorem, we can clarify like how actually the person is got a result. As the calculations are here using Bayes theorem, the numerator equal to 0.9 into 0.01, that means 0.009. The denominator P of positive equal to P of positive disease into P of disease plus P of positive with no disease into P of no disease, that equal to 0.9 into 0.01 plus 0.1 into 0.99, that equal to 0.009 plus 0.099, that equal to 0.108. So it is simple. As we just calculate the given values in the formula, you will get an answer. Even though the test is 90% accurate, the actual chance of having the disease after a test is only 8%. This example shows the power of Bayes theorem. It helps us reason correctly under uncertainty and avoid missing conclusions. So at next we'll see extending Bayes to machine learning. Now let's see how we move from medical testing to machine learning. In ML, instead of diseases and test results, we deal with the classes and features. So the same formula becomes P of class features, that equal to P of features of class into P of class by P of features. And our goal is simple: pick the class with the highest posterior probability. Think of a spam filter, like P of spam is free win versus P of not spam free win. So the algorithm calculates both and picks whichever is larger. So if we do this step by step, compute how likely each word feature is under each class, that's like likelihood. Multiply those by the class prior, that's P of class. Compare the resulting posteriors for all classes, choosing the one with higher probability. This process transforms simple word statistics into a full-fledged classification rule. So you can think of naive Bayes as a mathematical detective. It collects clues, that means features, weights their importance, and then decide which class best fits the evidence. So as we see the example, disease is H, class label is Y, symptoms E, features X, and P of disease symptoms. By that we'll take the features here, and if we go to next. Alright, now we have understood Bayes theorem and the naive independence assumption. Let's see how naive Bayes actually performs classification. Imagine you have a dataset, says a bunch of emails. Each email is represented as a set of features like contains the word free, has the word offer, includes the word meeting, and so on. So the goal is to figure out whether the email is spam or not spam. And mathematically, for any new input data x equal to x1, x2 up to xn, naive Bayes calculates the posterior probability of each possible class of y of k, which is likely spam or not spam. So the formula is look like that. As we see the formula here, and let's break down this. P of y k is the prior. How common that class is training data? For example, maybe 60% of emails are spam. So P of spam equal to 0.6. So P of xi yk is the likelihood, how likely each word or feature is given the class. For instance, how often offer appears in spam emails. So we multiply all these likelihood together with the prior. Okay, and the symbol alpha means proportional means proportional to. Since the denominator P of x is the same for all classes, we can ignore it while comparing. So after computing this for all classes, the algorithm picks the one of highest posterior probability, that's your prediction. And this is how naive Bayes transforms plain probabilities into a powerful classification decision rule. So if we take an example scenario of spam detection, let's make it more concentrate with the real world example, that is classic spam classifier. In this case, each word in an email becomes a feature and the classes are not spam and not spam. Suppose we have three keywords, free, offer and click. The algorithm first calculates P of spam and not spam and the class priors. And then we go for P of free, that is spam, and P of offer spam, P of click, that is spam. So this is the feature likelihood and similarity for not spam also. Now when a new email arrives with the words free, offer, click, and the model computes P of spam free offer proportional to P of spam into P of free mod spam into P of offer mod spam. So likewise we'll do with not spam also. Then it compares these two values, whichever is higher becomes the prediction. So if P of spam features greater than P of not spam features, the email is labeled as spam. What's interesting here is that every word contributes its own vote to the final decision. Even though free and offer often appear together, the naive Bayes classifier handles them as independent indicators and still manages to perform extremely well. That's the power of this algorithm. This same logic applies to product reviews like positive, negative, tweets like toxic, non toxic, and even medical diagnosis, disease present or absent. And the next slide, intuition behind it. Now let's build an intuition for how naive Bayes thinks. You can imagine naive Bayes as a voting system. Every feature or word is a probabilistic word for a particular class. Okay, and for example in spam detection, the word free votes strongly for spam, the word offer also votes for spam, the word meeting votes for not spam. Each of these words isn't just a yes or no, it's weighted by probability. Then naive Bayes multiplies all those words together, the class that's end up with the strongest combined probability wins. It's not adding words like 1 plus 1 plus, it's multiplying probabilities. Even a single strong clue can have huge influence. For example, if free has 0.9 probability of appearing in spam, that single feature can tilt the overall prediction quite heavily. So even though the features are treated independently here, their collective effect forms a confident decision, and that's why naive Bayes can work so efficiently. It uses simple math, but it'll build strong evidence based predictions. And now if we see the mathematical representation, let's summarize the naive Bayes math in clear and structured way. The classification revolves around three key probabilities like prior probability P of y, how frequent a class is in the training data. Example, if 60% of all emails are spam, P of spam equal to 0.6. Likelihood of P of xy is how likely we are to specific features given that class. Example, if P of free spam that equal to 0.9, meaning 90% of spam emails contain free. Posterior means P of y of yx, the final probability that the email is spam given the word contains. The relationship is simple here. Posterior proportional to prior into likelihood. During classification, the model calculates this for each class and picks the one with highest posterior probability. What makes this beautiful is that it mathematically grounded, interpretable and easy to compute. Even if you are a not math person, the idea is straightforward here. The model checks how likely your data is for each class, then picks the class that fit best. So naive Bayes don't guess, it reasons based on probabilities. Now if we move to the next slide, formula recap. So let's recap everything we have learned so far in the one neat formula, like as the given, where this is the formula like we are seeing. Sorry. So here, if we go for model variance overview, not we understand the working formula of naive Bayes. Let's talk about how something really interesting, that the different variants of the naive Bayes model. See, naive Bayes isn't just a single one algorithm. It's actually a family of classifiers all built on the same Bayes theorem foundation. The difference lies in how the model and the feature probabilities, that is how they calculate p of xi by y. Each version assumes is a different kind of data distribution, like Gaussian naive Bayes used for continuous data like height, weight or temperature. Multinomial naive Bayes used for count based data like word frequencies in text documents. Bernoulli naive Bayes used for binary data like whether a word is present or not. But remember, they all share the one core formula, and that is the formula they represent here. Only the way to calculate p of xi mod y changes depending on the data type. So when you are choosing a naive Bayes variant, you are basically deciding how to interpret your data. If your features are numbers, that means Gaussian. If your features are word counts, that means multinomial. If your features are yes or no, that means Bernoulli. This flexibility is what makes naive Bayes so versatile. It can adapt to different data types just by changing the distribution assumption. So not let's see one by one. So multinomial naive Bayes, which is specially popular in text classification tasks. This version assumes that feature represent counts or frequencies, like how many times a popular word appears in a document. For instance, if we are classifying emails, features could look like free means appears in 3 times, offer appears once, and meeting appears 0 times, and the formula for the likelihood based on the frequency of each feature. Example here, p of free offer mod spam equal to p of free mod spam, that means 3 times, into p of offer of spam mod spam, that is 1 time. Notice that we are raising the probability to the power of its count. So words that appear more often have more influence on the final prediction. In practice, so here 3 have more probability, so it has more influence. In practice, we often use a logarithmic form of this calculation to avoid numerical underflow when multiplying very small numbers. Why multinomial naive Bayes works so well means it models how often words appear, not just whether they appear. It fits perfectly with bag of words, the most common text preparation techniques or like NLP. So whenever you are dealing with word frequencies like email classification, news categorization, product review analysis, multinomial naive Bayes is best fit. And if we see the Bernoulli naive Bayes, which is slightly different from the multinomial one, while multinomial naive Bayes focuses on counts, but Bernoulli naive Bayes only cares about presence or absent. A feature is either there, one or not, that means 0. For example, in spam detection, you could represent an email as contains the word free 1 or 0, contains the word win 1 or 0, contains the word meeting 1 or 0. Then the likelihood formula becomes as the shown there. It basically multiplies the probability of present words and the complement probability of absent words. Example, if we take, if an email contains free and win, Bernoulli naive Bayes calculates how likely these two words are appear in spam emails regardless of how many times they occur. and so it's ideal for short text messages, binary attributes, yes or no type features. Think of Bernoulli naive Bayes model says that I don't care how often the words show up, I just want to know if it's there or not. This makes it perfect for datasets like spam filtering or sentiment classification on short reviews. Now, variant comparison. Here is a quick summary to compare all these three types of naive Bayes, which is crystal clear which one is used and when. So variant is Gaussian naive Bayes, that is data type is continuous data, and example use case is medical or sensor readings. And the key feature for this is features follow a normal distribution, and multinomial naive Bayes is count based data, text classification, document categorization, and features are word frequencies here. And Bernoulli naive is binary data like SMS, spam, short text classification. So features are 0 and 1 here. Despite their differences, they all compute probabilities using the same logic. As we see the formula here, the difference lies only in how each variant model the likelihood term, whether it's Gaussian, count based, or binary. So in summary, Gaussian means continuous numeric data, multinomial means word counts or frequency data, Bernoulli means presence or absence features. And that's the beauty of naive Bayes. One concept, three simpler variations, adaptable to almost any kind of data set. And if we see the next slide, training naive Bayes. Now that we understand the types of naive Bayes models, let's see how we actually train one. So the great thing about naive Bayes is that training it is simple, fast and non-iterative. Unlike other algorithms like logistic regression or neural networks, naive Bayes doesn't need gradient descent or back propagation. Instead, it only needs to estimate probabilities from training data, which means it basically just counting and dividing. The model learns two key types of probabilities, like class prior probabilities means this is how frequent each class is in the training dataset. Like if we take the formula here, p of yk equal to number of samples in the class k, total number of samples. Example, if we have 10 emails and 6 are spam, that means p of spam equal to 6 by 10, then we get the value is 0.6. As like feature likelihood probability, for each feature like a word and class like spam or not spam, we count like how often that feature appears in that class. Like if we take the formula here, like p of xi mod yk, frequency of feature I in class k by total features in the class k. Once we compute all these probabilities, we store them. That's a trained model. No complex updates, no tuning, just pure probability estimation based on the evidence. That's why naive Bayes is so fast to train and works even on large text datasets where counting is enough to capture the pattern. And if we see the next slide, like making predictions after training, prediction is even simpler. It's all about applying the base formula with the stored probabilities. Let's say we have a news email represented as x equal to x1 x2 xn for each possible class of yk, that means spam or not spam. The model computes the posterior probability based on the given formula. Then it compares the posterior probabilities for all classes and chooses the one that's highest. The final decision rule is called the maximum a posteriori map rule. So there we given a formula like, and example if we take here, if p of spam mod email equal to 0.82 and not spam email equal to 0.18, so prediction here is spam based. The best part, it's completely deterministic, there is no randomness or iterative updates because the chances of spam is 0.82. So we take the most probability. Advantages of this approach is no complex optimization, just multiplication and comparison, and instant prediction. That means suitable for real time systems like spam filters. Probabilistic output means you don't just get a label, you also get a confidence value like 82% spam. So this confidence score can be very useful in practical systems. For example, Gmail can decide whether to move an email directly to the spam folder or mark it as suspicious based on probability thresholds. So this is what how we make the predictions for naive Bayes. And if we go for the next slide, example calculation by taking the toy dataset. Now let's go through a simple toy dataset example to see naive Bayes in actions. Suppose we have total 10 emails, like 6 are spam and 4 is not spam. So priors are P of spam equal to 0.6 and P of not spam equal to 0.4. Now let's say the word free appears in 5 of 6 spam emails. P of free not spam equal to 5 by 6. And in one of the 4 non-spam emails, P of free by not spam equal to 1 by 4. A new email comes in and it contains the word free. Let's compute the posterior probabilities here. P of spam by free proportional to P of spam into P of free mod spam. So that equal to 0.6 into 5 by 6, that is 0.5 we get. So P of not spam mod free proportional to P of not spam into P of free not spam. So we take the same formula but for both scenarios, but we change the features here. Compare both, like 0.5 versus 0.1. So here spam means because it has the majority value, so the model predicts the email as spam. This small example clearly shows how even one strong word like free can dominate the decision. That's the intuitive power of naive Bayes. It doesn't need deep networks. So it doesn't need deep networks or large training data, just the right probabilities. Now if we go to next slide, there we have the zero probability problem. But wait, there is a small issue that can occur during training. What happens is here, if a particular feature never appears in a class during training. For example, if the word discount never appeared in the spam emails during training, then P of discount spam equal to 0. Now remember, naive Bayes multiplies all these probabilities together. So if even one of them is 0, the entire class probability collapses to 0. That means even if all other features strongly suggest spam, the final result becomes 0 because of the one missing word. So this is called zero frequency or zero probability problem, and it's quite common especially in the text data where vocabulary is huge and not every word appears in every class. So for instance, in a small dataset you might never have seen the word exclusive in spam emails, but in the real world it might be common. So if your model assigns zero probability to unseen words, it will make poor prediction when faced with the new data. So we need to fix that, and that's where Laplace smoothing comes in. So Laplace, that means add one smoothing. To solve the zero probability issue, we use a technique called Laplace smoothing and also known as add one smoothing. The idea is super simple. We pretend that every feature occurred at least once in every class, even if it is didn't in the training data. So instead of dividing it by 0, we just add 1 to every count. The modified formula becomes the P of xi mod y equal to count of features in the class plus 1 by total features in class plus n, when n is the total number of possible features, for example vocabulary size in text data. So if we take an example here, without smoothing, p of discount mod spam equal to 0 by 100, that means 0. So after smoothing, 0 plus 1 by 100 plus v, that equal to small but not 0. This tiny adjustment ensures that unseen features don't destroy our calculations. So benefits of Laplace smoothing is it avoids the zero multiplication errors and handles the unseen data perfectly, improves generalization, and it works for text and categorical features. So even if your model encounters a brand new word during prediction, it will still assign a small probability instead of crashing the entire prediction. That's how naive Bayes maintains stability and reliability even with imperfect or unseen data. So this is how we use Laplace for naive Bayes. And if we go for next slide, handling continuous versus categorical data. So far we have talked about a lot of about probabilities and variance, but in real world data sets we often deal with mixed data types. So features might be continuous like temperature, salary or age, and others might be categorical or binary like gender or is a word present. So how does naive Bayes handle that? Because the naive Bayes is flexible, we can mix and match models depending on feature types. So for continuous features, we can use Gaussian naive Bayes, which assumes a normal distribution. For categorical or count features, we use multinomial or Bernoulli naive Bayes. If your dataset has both, say a medical dataset where age is numeric and symptom present is categorical, we can combine both likelihoods. This forms what we call a hybrid naive Bayes model, which blends two approaches. For example, P of age mod disease equal to Gaussian likelihood, P of cause, so cough mod disease equal to Bernoulli likelihood. Then we multiply both probabilities to compute the overall posterior. So naive Bayes can easily handle a variety of datasets where there are purely numerical, purely categorical, or mix of both. That adaptability makes it a fantastic starting model in many applied ML projects. So as we take the differences here, data type is continuous for model used here is Gaussian naive Bayes, and how likelihood is computed means uses of mean, that means mu, and variance sigma squared to compute probability assuming normal distribution. And for categorical like multinomial or Bernoulli naive Bayes uses feature frequencies or binary presence values. And if we go for strengths of naive Bayes, now let's talk about why naive Bayes is such a beloved algorithm in machine learning. Even though it's old and simple, it's still used by major companies like Google and Microsoft in production systems. Here is why: because extremely fast to train and test, because no gradient descent, no iterative optimization, nothing, just counting and arithmetic. It's perfect for very large data sets, and it will works with small data set. Unlike neural networks that need thousands of samples, naive Bayes can perform well even with limited table data. Excellent for text and document classification, like handles high dimensional sparse data like bag of words, TF, IDF effortlessly. That's why it's so popular in spam detection and sentiment analysis. If we go for probabilistic and interpretable, it doesn't just give you a label, it tells you how confident it is. So you can easily explain it predictions, which is great for transparency and trust in AI. So in short, naive Bayes is simple, efficient, interpretable, and surprisingly powerful, a rare combination in the world of machine learning. So this is what the strengths of naive Bayes. If we go for limitations of naive Bayes, now of course no algorithm is perfect and naive Bayes has limitations too. Let's look at some key drawbacks we know when not to use it. Independent assumption. So it assumes that all features are independent given the class, but in reality, features often correlated. For example, in an email, free and offer often appear together. This correlation make neighbors probability estimates less accurate, and also struggles with correlated features. That means when features influence each other, that means neighbors may overcount or undercount their impact, and that time it will struggled and not great for continuous non-Gaussian data. If the continuous data doesn't follow a normal distribution, Gaussian neighbors can miscalculate the likelihood, and it needs the careful pre-processing like categorical encoding, smoothing and feature selection can strongly affect the results. So if we give the feature selection and categorical encoding smoothing perfectly, then it won't affect the results, right? Not ideal for complex and non-linear problems. It can't model intricate decision boundaries like SVMs or neural networks can. So, for example, in text data, neighbors can perform brilliantly. In image or speech data, it struggles since those patterns are deeply correlated and nonlinear. So, while neighbors is great baseline for complex problems, you'll need more advanced algorithms. So this is what the limitations of neighbors. And if we see the next slide, bias variance perspective. Here is an important theoretical viewpoint. Neighbors is a high bias low variance model. So let's unpack that. High bias means because of the independence assumption, neighbors doesn't try to learn complex patterns. It makes a simplified model of the world. That means it may overfit a little, it won't perfectly capture every subtle relationship, right? So low variance. But the advantage is that its predictions are very stable. Small changes in the training data doesn't cause big changes in the model's output. So naive Bayes is consistent and reliable even if it's not the most flexible one. In simpler terms, it may not always hit the bullseye because of high base, but it almost always lands near the center because of low variance. That's what it makes great for small data sets and real time systems where stability more matters than perfection. So here bias variance trade-off summary property in the table we see naive Bayes behavior. If the bias, that means high, variance means low, overfitting risk is low and underfitting risk is moderate. So this is what the bias variance perfect perspective. And if we see the next slide, scalability and efficiency, it is one of the biggest strengths of Naive is its scalability. It's built for speed and efficiency. Let's see why. Linear time complexity means the computations grow linearly with the number of samples and features. Number of samples and features means the things we are used in the dataset as the features, and that means if you double your dataset size, computation roughly doubles, right? No exponential growth. So it is the linear time complexity and the low memory usage. It doesn't store big matrices or weight vectors, only class pairs and conditional probabilities. Instant prediction means once trained, classification just involves a few multiplications, so predictions are nearly instantaneous. If we go for real world examples, email spam filters analyzing millions of emails daily, real time news categorization, or content tagging systems, because it's both fast and lightweight. Nairbase is ideal for real time analytics, streaming data, IoT and embedded systems. So if you ever need a quick, interpretable, and resource friendly model that delivers solid results, Nairbase is an excellent choice. Now, if we go for interpretability versus performance, like how it works, so let's talk about something every machine learning engineer faces: the trade-off between interpretability and performance. So some models like deep neural networks are incredibly powerful but often act as black boxes. You can't easily explain why they made a particular prediction. So naive Bayes on the other hand is the exact opposite. It's one of the most transparent and interpretable machine learning algorithms. So every probability term can be classified and inspected. So let me take the quick example. For example, the model can tell you P of free spam that equal to 0.9 and P of offer not spam that equal to 0.05. You can literally see why the model is predicting spam because the word free has a very strong association with that class. This interpretability is incredibly used for debugging models. You can check why a certain decision was made and building trust, especially in healthcare, finance, or legal systems where transparency is critical, explaining results to non technical stakeholders. So, the downside is because naive Bayes is simple, its accuracy may be slightly lower compared to advanced models like random forest or neural networks. But here is the key takeaway: when you need a model that's explainable, fast, and reliable, naive Bayes is often the perfect fit, even if it sacrifices a bit of predictive performance. And if we see the spam detection, let's start with one of the most application of naive Bayes is spam detection. In fact, this one of the major success stories of machine learning in real world use. Here is how it works. Every word in an email is treated as a feature, like um, gifts when you want, like these things. The model learns two set of possibilities, like p of word is spam and p of word is not spam. How likely the word appears in spam mails, that is p of word spam. P of word is not spam, like how likely it appears in regular emails. When a new email arrives, the model calculates as the given formula. If this value is higher than the corresponding, like p of spam words, the email is marked as spam. Example, if we take words like win, money, offer, and free have high probabilities under the spam class. So, if an email has multiple search words, the overall spam probability skyrockets. Why it works so well? Because the text data fits the independence assumption fairly well. It's fast enough for millions of emails per day. In fact, modern systems like Gmail and Outlook still use variants of Bayes as a core component of their spamming filtering pipelines, often combined with more complex models for extra. So now the next slide is document categorization. Next, explore another NLP task. This means automatically classifying documents into topics like sports, politics, technology, etc. The process is straightforward here. Like represent each document as a bag of words, just counts of how often each word appears, compute class probabilities like P of category of words proportional to P of category into P of word mod category. The class with the highest probability becomes the predicted category. So if we take an example here, words like match, goal, team strongly points to sports. Words like election, vote, policy indicates politics. Why it's effective means high dimensional data like thousands of words doesn't bother neighbors, it can handle them easily. Works great with TF and IDF features that weigh word importance. Achieves strong accuracy with minimal computation. So, applications include news categorization like Google News and search engines, automatic content tagging for blogs and websites. So, the sample principle, probability based reasoning, powers a range of NLP tasks from spam detection to document understanding. So now after this we have the medical diagnosis. Now let's move beyond text and talk about a life impacting application is medical diagnosis. In healthcare, decisions often involve uncertainty. Symptoms can overlap between multiple diseases. Naive Bayes helps handle this probabilistically. Here is Each symptom acts as a feature and each disease is a class label. The model computes P of disease of symptoms proportional to P of disease into P of symptoms of I mod disease. So example, symptoms of fever, cough, sore throat might indicate flu. As more evidence symptoms are added, the model updates its beliefs. The advantage is probabilistic approach is that it doesn't just say you have flu or not. It's a thing like P of flu equal to 85%, P of common cold equal to 10%, P of allergy equal to 5%. So doctors or systems can reason with probabilities instead of binary outcomes. So why it's useful means handles uncertain and overlapping evidence, works even when data is incomplete, simple enough for medical expert systems and chatbots. So if we go for real-time applications here, we have already seen many applications in text and healthcare, but naive bias is also used in real-world systems. Like examples include spam email filtering, instant classification as email arrive, like those are spam or not spam, and news feed filtering, like real-time categorization of articles or not, and recommendation systems, probabilistic interference for content suggestions, fraud detection, checking the transactions, like is there any issue with the transaction like frauds, all this. The key reason it works so well in real time is training is fast and straightforward, predictions are almost instantaneous, just a few multiplications. This efficiency makes it ideal for high throughput low latency environments, even on high large data sets. When naive bias shines means text classification, that means spam detection, sentiment analysis, and the document categorization, and small to medium data sets like performs well even when deep learning is overkill, and real time applications, fast prediction for streaming data, probabilistic insight needed when you need confidence scores for each prediction, high dimensional sparse data, like works brilliantly with thousands of features, especially text based data. So it is used for all these and domains we see here: emails filtering, NLP sentiment detection, news categorization, recommendation system. So in essence, nearby bias shines when you need speed, simplicity and interpretability more than the deep accuracy. Okay, so when we want the speed of model prediction and the simplicity of like no more congestion, so for all this we use naive bias. And if we go where naive bias fails means common failure cases and scenarios we see here: high correlated features, that means breaks the independence assumption, that means affecting the probability estimates. Like example, pixels in an image, like it will easily correlate the features, right? And continuous data without Gaussian distribution, that means Gaussian naive Bayes may produce inaccurate results, and complex non-linear relationships can't capture intricate patterns in data, and large vocabulary unseen in training, like zero frequency problem if Laplace smoothing is not applied. So these were all naive Bayes fails on, and in these scenarios more advanced models like random forest, gradient boosting, or neural networks may outperform neighbors. And here, better alternatives are for correlated or numeric logistic regression or random forest, for complex patterns, support vector mission or neural networks. And here we see the work how it works well and how there were fails on. And text and NLP it works well, and images, audio, time series it will fail because these data is complex to get, and it only mainly categories on categorical data, text data and numerical data, but these data may fail. And it works well on small data and fails on high correlated features, and it works on simple patterns but not in complex non-reliant data. So this is what the naive Bayes fails in. But if we see the final summary, let's summarize everything we have learned in the naive Bayes session. So core idea is probabilistic classifier based on Bayes theorem with a naive assumption of feature independence. It is a powerful machine learning algorithms in Bayes theorem, and the key variance here is Gaussian neighbors continuous features and multinomial neighbors is count frequency features, and Bernoulli is used for binary features, and this is what we use, and it widely used in text and NLP based applications such as spam detection, sentiment analysis, as we see many examples there. The model works well in small data sets as we previously discussed, and scales efficiently to large feature spaces. So, however, naive Bayes can struggle with when features are highly correlated on and when it is complex non-reliant relationships. That means more features or more data set, it will fail. So it's not ideal for image, audio, or deep structured data where advanced models like SVM or neural networks perform better on these types of data. So other types of data it works well, but in these types of data it will fail. And if we see the practical tips here, use Laplace smoothing to handle unseen features and choose the right variant based on your data type, and naive Bayes works best as a baseline or combination with other models. So summary and key takeaway is, finally here is the key takeaway you should remember, like probabilistic classifier, it means using of Bayes theorem to compute class probabilities and make data driven predictions. It's very better to take this. And naive assumption is assumes all features are independent given the class simple but effective. Based on the naive assumption, all independent classes are simple and effective, and strengths here, it is fast and easy to train. Yes, for categorical and the numerical and all those things, it has the three different types of approaches, so it will easily train, works well on text and NLP tasks, and performs reliably with small data sets as we previously discussed about this, and produce interpretable and transparent result. It gives the perfect results, and limitations are here is it doesn't perform well on correlated features and struggled with it, and not suited for complex or continuous data. Okay, and the best use cases are spam detection, sentiment analysis, document categorization, medical diagnosis, and real time system, as all these things are we previously discussed about it. And then and that brings us to end of this naive Bayes session. We started with the fundamentals of naive Bayes theorem, explored the core formula, discussed Gaussian, multinomial, Bernoulli variance, walked through training, prediction, and Laplace smoothing, and finally saw real world applications like spam detection, sentiment analysis, and medical diagnosis. I hope you now understand why naive Bayes is still widely used decades after it was first introduced. It's simply interpretable, fast, and surprisingly effective. If you found this video helpful, make sure to stay tuned because in the next session, my teammate will continue with more advanced AI and ML algorithms where we'll explore even more powerful techniques that build on these fundamentals. Keep experimenting, keep learning, and remember, probabilities are everywhere, and neighbor shows us how to reason with them. Thanks for watching, and I'll see you soon in the next session.